Welcome back to the Deep Dive. This is the place where we dig into complex technical sources to give you that essential knowledge you really need.
And today, we're settling some old arguments.
We really are. We're going beyond the high-level stuff, ignoring Python and C++ for a bit,
And getting right down to it.
right down to the fundamental language of the machine. What is actually happening in the transistors and registers of your CPU?
Our source for this deep dive is a really foundational work by Robert G. Plantz, Introduction to Computer Organization.
Subtitled, An Under-the-Hood Look at Hardware and on 8664 Assembly.
And our mission today is to really understand that full cycle of information, how physical switches encode data, how the hardware performs arithmetic with its limits, and how the whole system is built on pure mathematical logic.
Now, you might be sitting there thinking, I write JavaScript. Why do I care about assembly? But here's why this stuff actually matters.
It really does.
Understanding these foundational concepts, the capabilities, the limitations, it's the key to writing truly optimized code. It helps you debug those just bizarre errors that high-level languages hide from you.
It makes you a better programmer. It's the difference between, say, driving a car and actually understanding how the engine achieves combustion.
A perfect analogy. So let's start that journey at the absolute beginning. How does physical reality get translated into digital data?
It all starts with a switch.
The switch concept. It can be a big physical relay or a tiny, tiny transistor, but it only has two states, on or off.
Which we represent numerically with a bit, a 0 or a 1.
And while the bit is the atomic unit, we almost never deal with just one of them.
No, the smallest standard unit of memory is the byte. And in modern systems, that is always 8 bits.
Right, 8 bits. A nice, neat package.
Yeah.
But reading and writing long strings of ones and zeros it's just awful.
It's excruciating. If you're looking at a memory dump, you don't want to see 64 binary digits.
You go blind.
Which is why we need a human shorthand. And that shorthand is almost always hexadecimal, base 16.
And the beautiful thing about hex is that relationship to binary, right? 16 is 2 to the 4th power.
So one single hex digit perfectly summarizes 4 bits. It just compresses the information visually.
It's a huge mental shortcut. We talk about the decimal number 100. In binary, that's what, 0, 1, 1, 0, 0, 100.
Yep. But in hex, it's just 0 by 64. Beautifully concise.
It's all the same number, just a different way to write it. A more efficient way for us humans.
Exactly. And we should probably give a quick nod to octal base 8. You'll still see it sometimes.
Like in Linux file permissions, right?
That's the classic example. One octal digit covers 3 bits. But for memory, for registers, it's hex all the way.
Okay, so we have our 8-bit storage unit, the byte. Now, what does that pattern of zeros and ones actually mean?
That is the big question. Let's start with text.
So when you type something like hello world on your screen,
Those letters have to be stored. They're stored as an array of characters, and each character has a numeric code. We rely on ASCII, which is thankfully a clean subset of the modern standard, Unicode UTF-8.
and here's a critical piece of low-level knowledge, especially for anyone who's ever touched C or C++ mic. How does the computer know where that string of text ends?
The source material highlights this really elegant solution. C-style strings are just an array of characters that end with a special character.
The NUL character.
NUL character, U plus 0000. It's a byte of 8 zeros. It's a sentinel value, a marker that says, stop reading, the string is over.
And if you forget that NUL byte,
Your program just keeps on reading memory until it hits junk, or more likely, just crashes.
classic mistake.
Uh-huh.
Okay, so that's text. What about numbers? The simple way is just unsigned binary, right?
Right. The most straightforward way. You take 4 bytes, you get 32 bits, and you can store a number up to, 4.2 billion? Simple.
But the source introduces this other specialized format, binary coded decimal, or BCD.
BCD is fascinating because it seems so inefficient on the surface.
That was my exact question. The source points out you're basically wasting 6 possible bit patterns out of every 16. A 16-bit number in binary can go up to 65,535, but in BCD, it only holds up to 9,999.
So why the trade-off?
Exactly. Why?
It's all about precision and simple conversion. In BCD, every decimal digit 0 through 9 gets its own 4 bits. You store 1 as 0001, 9 as 1001.
So you're not doing complex binary math that carries across those 4-bit boundaries.
Precisely. And when you need to display that number or convert it to a character to print it, The conversion is trivial. The decimal structure is perfectly preserved.
Ah, so you avoid all that complicated binary to decimal math. That makes it perfect for old financial systems, COBOL applications, things where display accuracy was more important than, say, memory efficiency.
It's a great lesson. Sometimes efficiency isn't just about saving bytes.
So true. Speaking of memory, let's get into one of the most frustrating things for any low-level debugger.
Ah, yes. Endianness. The source calls this the official debugging aha moment.
It really is.
Yeah.
This is all about data that spans multiple bytes, like that 4-byte integer we mentioned. Memory is addressed sequentially, right? So the question is, which byte goes where?
Do you put the most important byte first or the least important byte?
And the common by8664 architecture that most of us use is Little Endian.
Little endian. The little byte, the least significant one, leads the way. It gets stored at the lowest memory address.
Which is exactly why memory dumps look backward when you're in a debugger like GDB. If
Totally.
you have the number 0 by 123 A5B, you read it left to right. But in memory, the first byte you see is 5B, then 3A, then 12.
It's so confusing until you train your brain to read it backwards.
The alternative is Big Endian, which you see in networking. They call it network byte order.
Right, the most significant byte is stored first at the lowest address. That's more human readable. But it means when your little endian laptop wants to send data over the network, it has to actively flip the byte order.
So data is stored, now for the real work, making it compute. And the next big hurdle is fixed with arithmetic.
This is the crunch point. Unlike math on paper, the computer can't just magically grow another digit when a number gets too big. The number of bits is fixed.
Now let's take an unsigned integer. In a 4-bit space, the biggest number is 15.
Right, and if you try to add, say, 14, which is 1110, and 4, which is 0100, the answer should be 18.
But 18 doesn't fit in 4 bits. The result you actually get is 00 narrow, which is 2. The math is completely wrong.
It would be, but the CPU gives us a signal. The hardware automatically sets a special flag, the carry flag, or CF.
And the CF is just a single bit that flips to 1 if the result of that addition overflows the space for an unsigned number.
Think of it like a car's odometer rolling over. The number goes back to 0, but a little light flashes to tell you it happened. The CF is that light.
That makes total sense for positive unsigned numbers.
Yeah.
But what about negative numbers? This brings us to 2's complement.
One of the most brilliant foundational ideas in all of computer science. Because a simple sign bit it breaks arithmetic.
It really does.
Mm-hmm.
If you try to add +2 and -2 with a simple sign bit, you get the wrong answer.
2's complement is the mathematical trick that lets the CPU use the exact same addition hardware for both signed and unsigned numbers. It's genius.
And the algorithm is so simple. To find the negative of a number, you just
Flip all the bits.
and then add 1.
That's it. Flip the bits and add 1.
Right.
That +1 is the magic step that makes it all work.
Now, when we're dealing with these signed numbers, the carry flag isn't what we care about anymore, is it?
No, the carry flag becomes irrelevant. For signed numbers, you need the overflow flag, the OF.
And the classic case for the OF is when you add 2 big positive numbers.
And the result wraps around and suddenly becomes negative.
That's the sign error. It means the result has gone out of the valid range for a signed number of that bit width.
Exactly. The OF gets set to 1 when the signed result is out of range. The hardware figures this out by looking at the carries into and out of the signed bit.
We don't need to get into the whole XOR rule here, but the takeaway is clear. The hardware signals that the signed bit got corrupted.
So here's the ultimate critical thinking moment from the source. Both the carry flag and the overflow flag are set by the CPU hardware during every single arithmetic operation.
The hardware is agnostic. It doesn't know if your variable is signed or unsigned.
It's just doing the math and setting the flags. It's the software, your code, the compiler that decides which flag is relevant.
So if you're working with unsigned integers, you check the CF and ignore the OF.
And if you're working with signed integers, you check the OF and ignore the CF. That distinction is entirely up to the programmer.
Okay, so we've covered storage and the limits of arithmetic. Now let's go even deeper. Everything we've talked about, all of it, is built on the fundamental principles of mathematical logic.
This is where we bridge from arithmetic to the actual hardware. George Boole formalizes Boolean algebra in the 19th century, true and false, 1 and 0.
But the real genius was Claude Shannon.
Yes. In the 1930s, Shannon had this incredible insight that Boole's abstract logic perfectly mapped onto physical electrical switches.
That idea that logic dictates wiring is the foundation of every digital circuit ever made.
And it all boils down to 3 fundamental operators.
AND, OR, and NOT.
And they have some properties that are a little different from regular math. And D is kind of like multiplication. Anything A and D 0 is 0.
Right, that's the annulment value. But with OR, which is like addition, the annulment value is 1. Anything OR 1 is always 1.
And that's a powerful shortcut in logic. But here's the one that really trips people up. In Boolean algebra, OR is distributive over A and D.
Which is the opposite of what we learn in school.
It is. The fact that XOR Y A and Z is the same as XOR Y and D XOR Z is this amazing mathematical gift for circuit designers.
Which brings us to De Morgan's law. It's a perfect example of the principle of duality in logic.
It is. It says that negating the A and D of two things is the same as the OR of their negation.
So not X and Y is the same as not X or not Y.
And that principle of duality means for any logical expression, you can find an equally valid dual expression just by swapping A and Ds and ORs and zeros and ones.
So why do engineers care about having two ways to build the same thing?
Minimization. It's all about efficiency. Every one of those A and Ds, ORs, and knots is a physical logic gate on the chip. If you can simplify the logical expression,
You simplify the physical circuit, fewer gates.
which means lower cost, smaller size, and crucially, less power consumption. The goal is always to find the minimal expression, the one that... It's the simple logical rule. The carry is 1 if at least 2 of the inputs are 1. This minimal version reduces the number of gates, reduces the inputs to those gates. It's the difference between a slow, power-hungry circuit and a fast, efficient one.
That is a real journey. We started with a physical switch. We saw how binary encoding gives it meaning. We grappled with the physical limits of arithmetic using the CF and OF flags.
And we end up realizing that it's all governed by Boolean algebra, which lets engineers optimize these circuits down to the bare minimum.
It just connects every single layer. Your abstract high-level code gets compiled down to machine code that depends on these physical operations.
Which are themselves designed using these pure mathematical laws.
So we talked about that principle of duality, that you have these two equivalent forms, the sum of min terms, which optimizes for the true cases, and the product of max terms, which optimizes for the false cases.
And that leads to a final provocative thought for you. It sits right at that intersection of math and engineering.
Okay, let's hear it.
We usually assume the goal is just to find the shortest algebraic expression. But the final choice, whether to implement a circuit using the minimal sum of products or the minimal product of sums, often doesn't come down to which one is shorter on paper.
So what does it come down to?
The hardware engineer often picks the form that best uses the specific types of logic gates they have available, or what fits the physical layout constraints on the chip.
Ah, so even if one expression looks a bit shorter, they might choose the other one if it allows them to use fewer chips or arrange things more cleanly on the silicon.
Exactly. The math is equivalent, but the physical reality, the engineering constraints, might demand what looks like the longer algebraic form. It's a constant negotiation between mathematical purity and physical pragmatism.
That is fascinating. Thank you for joining us for this deep dive into the very core of computer organization. We'll see you next time.